Thank you all for coming bright and early to this Friday morning session here at reInvent. I hope you've had a good week. My name is Tony Gibbs, and I'm a database specialist solution architect here with Amazon Web Services. This talk is primarily about Nielsen's journey to Amazon Redshift and what they had to do to migrate that workload up to the cloud. And I'm happy to have TJ's who is the VP of Technology at Nielsen here, to present that journey. Before we get started, I'm going to go through just kind of the introductions to Redshift, what it is, architecture and concepts, that sort of thing. I'm going to give you some tips on how you can accelerate your data warehousing migration to Amazon Redshift, and then I'm going to hand the presentation off. We'll wrap up with just giving you guys some additional learnings at the end. I don't know if we're going to do open Q&A in here. I don't think the microphones are set up for that, but we will do Q&A off to the side or outside the room, actually, after the session is complete. So just to see where you guys are at, how many of you are using Redshift today? Okay, that's more than I actually thought. How many of you are looking to migrate to Amazon Redshift? Okay. That was kind of what I was more expecting. So it's like half and half. Redshift, for those of you who haven't used it before, it's an ANSI SQL ACID-compliant data warehouse. It's incredibly fast, and when we launched Redshift, we aimed to reduce the cost of data warehousing by we want it to be 1/10 of the cost of what traditional data warehousing was at the time. Redshift also integrates with a data lake, which is one of the important concepts that we have. So a lot of customers are building out these data lakes now on Amazon S3, and Redshift cleanly integrates with data lakes. And I'll talk about how we do that in a couple slides. We've increased the performance of Redshift dramatically over the last couple of years. In the last year alone, Redshift has seen close to a 3x or 4x performance improvement. And we've continued to drive down the cost of Redshift on a price performance basis. And I'll talk about the new instance type that we recently launched actually on Tuesday earlier this week. Redshift is highly scalable. You can scale it up in a matter of minutes, adding or removing nodes. And now that we've effectively separated compute and storage, you can continue to add data to a Redshift cluster without adding additional nodes. It's obviously fully managed, which means we take care of Redshift. And it is also, most importantly, secure. So if you have workloads that require things like PCI, HIPAA, FedRAMP, or other certificates, Redshift also has that. It encrypts data at rest if you turn that on, and it also encrypts data in flight as well. So let's talk about where Redshift came from. It was originally came from Postgres, so the SQL syntax in Redshift is very similar to Postgres. We entirely rewrote the back end, though. It's a Columnar storage engine, so 100% rewritten. It's also MPP, which means that Redshift can scale out horizontally. We added a lot of OLAP functionality to Redshift. So these are things like windowing functions, approximate functions, a lot of the functionality that you use in an analytics database. And we continue to add more functions over time. We just launched geospatial support, so we added over 40 new functions to support geospatial, as well as the geometry data type that goes along with that. We wrapped all of this up in AWS, so this is integration with other services such as IAM for authentication, S3, which is where you typically load data and unload it. We also have integration with KMS, that's what we use for the encryption of your data at rest. And it is all of the combination of these things that make Redshift what it is. We roll patches out to Redshift every 2 weeks. It's a 2-week cadence. It's a managed service, so we take care of that. Any security updates that need to happen, automatic. We take care of all of those things. You just set a 30-minute maintenance window at any time that works for you, and that's when we roll those out. The last 18 months in particular have been really exciting for the Redshift service. We've launched over 200 new features and enhancements in the last 18 months alone. The Amazon Redshift architecture, it's an MPP share nothing architecture. I'm going to start by explaining it up at that green box up at the top, which is a SQL client and BI tools. So you can connect to Redshift using JDBC or ODBC drivers that are supplied by AWS. Or if you're using another programming language like maybe Python or R or Ruby or something like that, you can also use the open source Postgres drivers with Redshift as well. You connect to this top blue box up there called the leader node. The leader node acts as your query coordinator. It does any final steps in the aggregation, and it communicates with all of the compute nodes which are underneath it. In this example, I have 3 compute nodes, but you can have anywhere between 2 and 128 of these compute nodes. Redshift can now scale up to 8.2 petabytes of raw storage. All of your data resides in those compute nodes or in managed storage, which I'll talk about on the next slide. And each one of those compute nodes executes a query against the data that belongs to it. And all of that happens entirely in parallel. Then the results from each compute node are sent up to the leader node. The leader node does any final steps in the aggregation, maybe an order by, that sort of thing, and returns the data up through your driver to whatever BI tool you happen to be using. Underneath the compute nodes, we have S3 there, and that's typically how you either load data or unload data. Then in the background, the Redshift service also is synchronizing data continually to S3 because the backups are automatically taken care of for you. So Redshift's always asynchronously synchronizing that data to S3. You can also launch a restore or a new cluster off of those snapshots if you want at any time. So if you had like another team that wanted to just do some experimentation, they could create a Redshift cluster off of that snapshot, do their experiments, shut it down, stop paying for it. 2.5 years ago, we launched Amazon Redshift Spectrum, which is this layer that sits in between your compute nodes and S3. It's a highly scalable layer of compute that's provisioned at query time. So what happens is you can store data on S3 in an open format like Parquet or ORC or JSON or Avro, and you can expose that raw data in S3 to your Redshift cluster as an external table and query it with this Spectrum layer that is spun up dynamically at query time and executes the query for you and passes the results into your Redshift cluster. You can even join data on S3 with data that's in your cluster. So it makes integration with a data lake much easier, and you can, some customers also use it to offload data to reduce cost in their cluster. So let's talk about the evolution of the Redshift architecture. This is what we released on Tuesday. All of the same parts of Redshift that I just explained are there, but we've now introduced Redshift Managed Storage. And what Redshift Managed Storage is it's a combination of SSDs and S3. Redshift takes care of the movement of the data to make sure the hottest data resides in the SSDs. And it effectively allows you to scale a compute node up to 64 terabytes of storage. We also announced what we call Aqua. Aqua is essentially AWS hardware, designed hardware, that we are pushing down close to that compute to take care of things like compression and encryption and doing additional filtering and predicates and in accelerating that and reducing the amount of data that we need to transfer within the Amazon Managed Storage layer. So these are previously we had 2 data instance types. I'll talk about those quickly, and then I'll talk a little bit more about the new RA3 instances, which are what we released earlier this week. So the DC2, or Dense Compute 2, was our solid-state backed instance type. That was our high-performance instance that if you needed a heavy or a large amount of compute, you typically used the DC2s. Then we had our dense storage, which was magnetic disk-backed storage. And those were the 2 kind of instance types that you would either pick between depending on your needs. Now that we have the new RA3 instances, now you can provision the amount of compute you need, and will dynamically in the background provision and manage the amount of storage that you need to go along with that. We'll still have a lot of customers that will still use DC2 and DS2, but I think going forward, a lot of customers are probably going to move towards the new RA3s with the separated storage and compute. So I'm going to introduce you guys to Columnar. This is a pretty simple concept. Redshift, like I mentioned, is a Columnar data warehouse. The reason we use a Columnar architecture is to reduce I/O. The types of queries that you typically execute on a data warehouse usually just querying a small set of the columns. So you might have a table, for example, that has 200 columns, and you're probably going to only query, might be a dozen of those columns at a time, and you're going to be doing aggregates across many millions of records. Those sorts of operations perform better in a Columnar architecture than, say, a row-based database like Postgres. Just to illustrate this, say we have this table here. It's a deep dive table. I have a few sample records there. And I have this very simple SQL query where I want to select and find the minimum date in this table. Now, in a row-based database like Postgres, assuming I don't have an index to help out, I would have to scan through all of the data in that table. In Redshift, on the other hand, I can just read through that date column only, like that, and I reduce the amount of I/O done on this query. And so that's the reason we use a Columnar architecture in Redshift. Now, a little bit about compression. Compression is really important in Redshift. We usually apply it automatically, or Redshift will do its best to automatically apply it. It has two goals. The first and most important goal is that it dramatically reduces the cost for you. We usually get somewhere closer to 4 times compression in Redshift. And that allows you to obviously store significantly more data in your cluster, especially with the RA instances. That reduces your cost essentially on the storage piece by 4. It also improves performance. So in Redshift, I/O in a lot of cases, for a lot of customers, is still the bottleneck. So if we're able to reduce the amount of I/O that Redshift does, that will improve performance. So let's simple example here. I have this deep dive table, the same one I used in the previous example, some sample rows here. What you can see here is if I modify the DDL there in red, you can see how I've put these encode statements in here. The compression is applied on a column by column basis. So that means each column in the table can grow and shrink independently from each other column, and we can apply the optimal encoding type or compression for that particular data. So the next piece is blocks. Blocks are a really important concept in that they are, or the important concept to know about them is they are immutable. We never go back, we never change an existing block. They're essentially append only in the underlying system. They're obviously encoded with one of 13 different encoding types, and a full block in Redshift can actually contain and hold up to in the millions of values. Usually I see blocks holding several 100,000 records, but in certain cases, if you're getting really good compression, it can be in the millions. Zone maps are the next piece of terminology I introduce you to. The purpose of these is to eliminate unnecessary I/O, and we do this by checking an in-memory data structure that stores the minimum and maximum value for every single block we have in the cluster. So Redshift automatically keeps track of these min and max values for every block, and then at query time, it will check them. So if there's a predicate, it'll check those, and it'll use that information to reduce the amount of I/O that it needs to do. So the next piece is data sorting. The purpose of data sorting in Redshift is to make the zone maps more effective. So we have those zone maps, those min and max values. If I were to sort, say, a table, that in certain cases can make the zone maps more effective. And I'll illustrate that in 2 more slides. So just to go through sorting, same deep dive table, same set of rows. If I were to apply a sort key to this, and I've changed the DDL up there in red, and I sort this table first by the date and then by the location, what we're going to see here is sorted first by the date. Now we have this tie here, and it's going to go over to the location, and JFK comes before SFO, and that's how the sort order in Redshift would apply to this particular table if I were to put that sort key on this table. Now, tying all of these concepts together, zone maps, sorting, we say we had this unsorted table here. And I have come along with this very simple SQL query. I'm just counting the number of records on this particular day. What Redshift's going to do is it's going to check the zone maps, like I mentioned, and it's going to reduce I/O in the cluster. It knows it doesn't need to read data out of that one block on disk. Now, if I were to take this exact same table and sort it by the date, you can see that those zone maps there on the right that are printing out those min and max values, they're now in sequential order because the table is sorted by that. We can now further reduce the amount of I/O that we need to do. And that's the primary purpose of sorting data in a Redshift cluster. So the next piece of terminology is slices. The easiest way to think of slices is they're essentially virtual compute nodes, and it's how we get parallelism within each one of our nodes. So our compute nodes are divvied up into a certain number of slices. It's either 2 or 16, depending on the size of our node. And that's how we get the parallelism within it. The other interesting thing is that the data is stored on a slice-by-slice basis. So how do we distribute the data to these slices or tell Redshift how to spread the data out? We have a few different techniques for that. The first is distribution style by key. What we essentially do is we take you assign a particular column to be the distribution key. We look at the value for each row for that column. We hash it, and that hash corresponds to one of the slices in the cluster, and that's where the data goes. The next distribution style is even, and what even is it's like saying to Redshift, I don't know what to pick for a distribution key, but just please evenly spread the data across the cluster. And Redshift just automatically round robins the data across the nodes. The next one is distyle all. What distyle all is it's kind of a special case one for if you have small tables. Usually they're dimension tables. You're usually doing a lot of joins to them. And what it does is it duplicates and it makes a complete copy of that table on each one of the nodes in the cluster. The last one is distyle auto, and it really is just a combination of even and all. And what happens is when Redshift, if you say we're writing data out to your Redshift cluster and it's a small amount of data, Redshift will automatically set the table to all. And then when it passes a certain threshold in size, Redshift will convert that table into distyle even for you automatically. So let's go through a couple examples here of how these distribution styles work. It's the same deep dive table. It's the same rows. We'll just say we have those 4 rows. And I have these 2 nodes down there, and each one of the nodes is comprised of 2 slices. So with distyle even, the data is just going to evenly round robin through each one of the slices. So you can see all 4 rows just spread across those 4 slices. If I were to switch this to, we'll say, distyle key by location, so that's those values, SFO, JFK, SFO, JFK, what we're going to see is SFO might correspond to this slice, JFK over there. SFO is going to go back to that slice 0, and JFK is going to go back to slice 1 because of the same values. And this is an example of a bad distribution key. The reason why is if I were to execute a query against this cluster, there's no data on node 2. We're essentially wasting that compute node. It won't do anything. So we want to pick a column that has high cardinality, something maybe even that looks like a primary key. So I'm going to pick this audience ID instead. And you can see the DDL has been modified. And now it's 1, 2, 3, 4. 1 might hash there, and 2 over there, maybe 3 over there, and 4 there. I obviously cooked the example with 4 rows and made it work perfect. But if you have millions of records, it's going to tend to work out that the data is going to be evenly spread if it's some high cardinality value like that. So distyle all, what we do with this is, as each record comes into the table, we write it out to the first slice on each node. So that's how we implemented that. So just to kind of reiterate on what these are for and why you'd be picking each one, distyle key is primarily used for joins. So if you're writing on a SQL statement, you have a join, wherever that on clause is, that is what the 2 tables that you're joining on, that column that you're joining on, that's typically what you want to distribute both of those tables by. Now, you don't want to cause any skew, like in the example where I had up there where all the data landed on one node. And you can check the skew with that SQL query there. It's svv_table_info. That's the table that contains the information about the skew. And there's this ratio in there. That ratio is, if I were to take the slice with the most data and compare it to the slice with the least amount of data, that's what that ratio is. Ideally, it should be close to 1. If it's 1.1, 1.2, 1.3, totally fine. Once it starts reaching, say, like 2, that means you have a slice that contains twice as much data as another slice. And that's probably not going to work out that well. The next reason to have a distribution key is if you're inserting data and selecting it out of another table. I typically see this when, say you're using staging tables. And you have a staging table and you have a production table, and you load data into the staging table and you copy it in your production table. If those two tables have the same distribution key, that copy of data is going to be significantly faster. With dist_style_all, like I mentioned, it's meant for smaller tables. We define a small table in Redshift as being about 3-ish million records or less. I've seen some customers have success even making 5 million records, but as a rule of thumb, if it's 3 million rows or less, you can usually use dist_style_all for that table. Now, we have dist_style_even, which I talked about. That's the really simple one. If you don't know what to do, that's a safe one to pick. Dist_style_auto is the new default in Redshift. So if you create a table and you do not define any form of distribution at all, Redshift is going to default to dist_style_auto. So a couple tools here help out with accelerating migrations. The first one is the Schema Conversion Tool, or SCT. It's a standalone application. You can install it on even your laptop, desktop, on an EC2 instance. It essentially allows you to point the tool to a target database and to a source database, and it converts the schema for you. It can also do a one-time movement of data, which I'll talk about as well. Then we have DMS, which is our data migration service. It's essentially a replication service that allows you to point to a source and to a target, which could be Redshift, and essentially do CDC replication between the two databases. And this can be really nice when you're doing a migration and you have maybe a proof of concept cluster up and you're wanting to stream that data over and keep a running total of, or keeping things up to date in that proof of concept cluster. So we'll go a little bit deeper into SCT here. The top piece up there is, I love this feature when I'm working with a customer, is sometimes we'll have them install SCT, run the tool, and what it'll do is it doesn't need to even do the conversion, but it can do an assessment report. And it'll give you an idea of how difficult the migration is going to be. For example, some databases might have a lot of PL SQL in it, depending on what you're coming from, or some sort of stored procedures, and it'll flag how much of that there is. Maybe you have binary objects in your data warehouse. I don't usually recommend that, but sometimes customers have that. And so it'll go through and it'll see what can be converted and the amount of effort it is, and it's a really nice report to have. SCT also saves a ton of typing, especially if you have you're coming from a database and maybe the data types names are just slightly different than Redshift, and you don't want to have to write out a whole bunch of grep commands. This tool saves a ton of typing, and I highly recommend using it just to get, like I said, at least the assessment report. The other thing SCT can do is that one-time movement. So what we have for that is you install these extractors, and you can install them usually on maybe an EC2 instance or somewhere. You can install them really anywhere. And what they do is they will reach out to your source database after you've converted the schema, and it will move the data across the line into your Redshift cluster. It can also drop the data locally as well, and what some customers will do is they'll order up, say, like a Snowball Edge, for example. They'll extract the data if they have a lot, like if it's 50 plus terabytes, and they'll extract that data, drop it on a Snowball, send that Snowball up to AWS. We'll drop the data in S3, and then you can continue loading that data into Redshift. You can see some of the databases or traditional data warehouses that SCT supports there. So data migration service, like I mentioned, it's usually when people are using it for Redshift, they're doing the replication and wanting to keep things continuously up to date. So these are just a handful of tricks and kind of tips and stuff that I've run into over the years while working and helping customers with Redshift. When moving from a traditional database, if it's a row-based database, I find a lot of times we have these highly normalized table structures. Redshift, being Columnar, really likes if you denormalize the tables. So for a lot of times, really wide fact tables, and really kind of sometimes getting even rid of date dimension tables. I know those are in a lot of traditional databases. You have these date dimension tables. In a lot of cases, it makes sense to take those values, put them into your Redshift cluster. And the reason why is because we really want to leverage those zone maps that I talked about earlier in your Redshift cluster. The other thing to be aware of is distribution. A lot of data warehouses, if they only run on a single node or a single server, there isn't really a concept of distributing data. So that's just something to be aware of, which is why I covered it. The other thing is we also released earlier this year PLPG SQL stored procedures. It was a huge request from customers that were doing migrations from other databases where they had large amounts of this code, and we would always have to tell them they had to extract that out, maybe put it into Glue or somewhere else, rewrite it in Python. So now you have a bit of a path to actually port your stored procedures over to Amazon Redshift. Now, I am going to hand the presentation off here, and you guys are going to hear Nielsen's journey. Thank you.
All right, just checking the mic. All right, good. So thank you, Tony. As Tony said earlier, I'm Tejas Desai. I lead the technology teams at Nielsen for our TV measurement products. Before I get into our specific use case, let me give you a little background on who is Nielsen, what it is that we do, and what exactly I mean when I say TV measurement. Nielsen is the arbiter of truth in the world of media. We produce unbiased data sets that drive buying and selling of ads, pricing of content, as well as distribution deals. What that essentially means is that we're that independent referee that sits in the middle, and we produce the data and analysis that enables decisions. The foundation of what we do as a result is we measure the consumer. We measure what they watch, how they watch, what advertisements they're exposed to. And really the holy grail around all of this is to measure everyone, everywhere. Because if you think of what is TV measurement, that in itself has really evolved over time. You have Disney Plus that just launched their streaming service. Apple just did the same. NBC is going to be doing that next year. What that means is how content is consumed is evolving. The total volume of content is increasing. And that is where our use case really comes into play, because with that increase in content, our technology, our platforms have to evolve. We have to evolve to scale up to the additional volumes that are coming in. We have to evolve to support the ever-changing and more complex methodologies that are applied on that data. And that's where our national TV audience measurement comes into play for this use case. So let me give you just a high-level overview of this platform, which will kind of help you understand then where this migration and this use case fits in the bigger picture. If you think of our national TV audience measurement platform, it really kind of boils down to three high-level components. At the far left, we have our systems that collect this data. In the middle, we have our processing systems that take this data, enrich it, harmonize it, apply our methodology on it, and essentially prepare it so that it can be consumed by our client-facing applications through which we deliver all of our insights. And it's the component that you see in the middle, the data processing component, that we're really going to talk about today, because this is what really sits at the heart of our entire measurement. So let's talk a little bit about where we were at the start of this journey. Prior to the migration, we had an on-prem data warehouse, several years old. It was great for what it was designed for at the time, but as I said, our data was changing, ever increasing, our methodologies are changing, and we needed to evolve with it. And with that, our technology needed to evolve. What had also happened over time is that this had turned into a bit of a monolithic architecture. We had dozens upon dozens of processes and procedures that were kind of interleaved with lots of dependencies, which you can imagine becomes a bit of a challenge when you're trying to manage and scale something like this. We were also starting to hit some limits on scale with the additional volume coming in. We were a bit hardware constrained with what we had, and we just didn't have the elasticity and scale we needed with that solution. And the other aspect of it was that our broader platform was also modernizing and moving to cloud, which means if you look at the upstream systems and downstream systems, they were starting their own cloud journey. And we didn't really want to stay in that hybrid state for too long, where we're taking data from the cloud, moving it to on-prem, moving it back to cloud. It just created a very inefficient way of really running the platform. So these were really some of our key drivers for starting this journey. So how did we approach this migration? It happened in 5 phases. First and foremost, we had to really break up the monolith that we had and really move away from a set of processes and procedures to really a service-oriented architecture. So certainly not looking to just do a lift and shift from one warehouse to another, but really rethink what it is that we were doing within the solution that was there in the first place on-prem, and really redesign it so that we leverage the right technologies that fit the use case. Second, we wanted to right-size the solution. With the on-prem architecture that we had, you kind of always tend to size up your hardware to your worst-case scenario, which is not what really happens every day, right? So we really wanted to leverage what AWS had to offer so that we could right-size for that sunny day and easily scale up and down as the worst-case scenarios materialized. So in parallel, we went through a lot of performance tuning and scaling. Additionally, we had a wide set of supporting services on-prem around this warehouse that did everything from orchestration, monitoring, alerting, logging. So we had to rethink all those services in terms of what they would look like in this cloud-based architecture. And last but not least, we had to go live. Design is great, architecture is great, development is great, but you eventually have to take this thing live, and you're talking about 12 terabytes of data moving to cloud, and this thing has to go live seamlessly in the middle of a daily production that runs throughout the day. And frankly, our clients don't care if that data came from on-prem or cloud. They care that it comes out on time and it's correct. So there was quite a bit of coordination that had to happen, that this actually happens seamlessly on the day we actually went live. So let's talk about that first phase a little bit. How do you break up that monolith? Like I said in the beginning, we don't want to just lift and shift, right? So where we started is we invested quite a bit of time in actually profiling all the procedures and processes that we had on our on-prem warehouse and started logically grouping them by what services they were actually supporting, what business use cases they were actually supporting. And that immediately bubbled up 2 patterns for us. One, we had a set of services that were heavily dependent on a long tail of data going back days, weeks, months that we run analysis on a daily basis. And we run this within a very tight SLA. So what we really needed was a persistent solution like Redshift, where we persist that data, we incrementally load on that data, and we can run through all these services within a very narrow window and run all the analysis we need to. The other group were really a set of processes that were one-off batch processes very short-lived. You're running a very small amount of queries on this data. And we ended up picking a more ephemeral solution, which was specifically EMR on Spark. So for those cases, we were actually able to leverage a technology that was offered to us where we could just spin up the cluster when we needed it, spin it down, and move on. And this is kind of what I meant by earlier on when I said that we didn't want to just lift and shift. We didn't want to just go from one warehouse to another, but really rethink and leverage the wide set of technologies available to us so we kind of start the journey of right-sizing the solution and moving it to the right technology based on the use case. Next step for us is right-sizing, and really the right-sizing and the performance tuning kind of go hand in hand. So I see them really kind of parallel set of activities, but as I said, first and foremost what we wanted to do was make sure that now that we were no longer hardware constrained and always planning for the worst case, we wanted to really understand what is that minimal use case that we need to target for on a daily basis, and then what is that maximum use case we want to scale up to. So this gets a bit tricky, right? You have this on-prem warehouse, you've got this large box that tends to somewhat almost mask some of the inefficiencies you might have for some of the other queries, other processes you've built that are built for that sunny day, but you have all this CPU capacity and memory that can kind of make up for any inefficiencies you have along the way. So the first thing we actually had to do was start establishing a baseline. We had some baselines from other migrations that some other parts of our platform that had gone through this migration over to Redshift, and what we decided to do was kind of leverage some of their baselines, and from what we had there, we knew that dense storage EC2 instances had worked pretty well for them. So what we started doing was we actually started loading small chunks of our data, starting with a couple of days, couple of weeks, couple of months, and started profiling all the processes we had moved over on that class of instances. Initially performed extremely well, but what we realized is as we loaded more and more data, that performance kind of started degrading. So this is where we actually started engaging a lot of the AWS solution architects. And they were actually able to help us quite a bit on analyzing the profile of the queries, and what we actually very quickly realized was that we had run into a I/O bottleneck as our data set started growing. And really the main reason was the nature of our queries and processes requires us to go back to a lot of the data that goes back pretty far historically, and this continuous process of going back to read the data was starting to create this I/O bottleneck. So we very quickly, as a result, ended up moving to the DC2 class of instances where you had SSDs available that just immediately started removing this I/O constraint that we had. Along the way, this also helped us kind of start to understand what our minimal configuration looked like and started supporting the performance tuning and scaling exercise that we were going through in parallel. So in terms of performance tuning, the first thing we did was, again, we worked with a lot of the AWS architects to optimize our code repository and fine-tune it. Next, we had to start going through all of our tables, all of our columns, and started doing a lot of what Tony was referring to earlier in terms of figuring out what is the right combination of distribution and sort keys that were going to be optimal for us. The one thing to understand about our data is that it's very rich and it's very complex. What that means is there aren't really 1, 2, 3, 4, or even half a dozen or dozen dimensions on which we can really analyze this data. There's actually dozens upon dozens of dimensions across which you want to cut this data. So as a result, what you can see is even distribution was really ideal for us, and that's actually what we ended up applying across majority of our tables. Having this in place, the next thing we actually started doing was, through the same profiling exercise, we started looking at which tables and which columns were being read more often, were being changed more often. And as a result, we were able to figure out where the higher risk of fragmentation was. So we were able to come up with a robust grooming strategy around it based on that exercise. And then, based on that, we were also able to figure out which columns and tables were really the best candidates for compression based on our requirements for the SLA we were trying to hit in terms of within what time window we have to run through all our processes in a day. So now that we had this design for our architecture in place, it was time to build out all of the supporting services that run this part of our end-to-end flow. As part of our broader platform, we use Airflow for our end-to-end orchestration, and for us in this case, that was very valuable. We had to go and write a bunch of custom operators because we have quite a bit of daily ETL that brings in our daily incremental data into Redshift. So we did quite a bit of work to build those operators out, and we leverage Airflow heavily to manage our end-to-end orchestration, not just for the ETL for Redshift, but also to bring up and tear down all the EMR clusters for the other set of processes that I talked about. Beyond that, we also had to do quite a bit of development where we take all of our logs that come out of Redshift, we pipe them into our monitoring services, logging services such as Logstash, Kibana, Elasticsearch, and then we also integrated PagerDuty, which is very critical for us in terms of alerting all of our support teams that tend to be on call essentially 24/7. Last but not least, we had to come up with a robust strategy for data quality checks. So one thing about Nielsen is the quality of our data is of the utmost importance. Remember what I said earlier, we're basically the currency in the TV world on which all the ad dollars trade, right? So for us, it's extremely important that the data is correct. And while this is not the client-facing application, we do everything we can to make sure that the data is correct before it even reaches that client-facing application. So what we ended up doing is, obviously, we don't run these DQA checks directly on the Redshift cluster in the middle of our daily processing, because while one phase of it may be done, there's another phase coming up right after it. So what we actually do is, after each phase of our processing completes, we bring that data onto S3, and we actually leverage Athena to query all that data and run through all of our DQA checks. And this in itself is a highly automated process, which allows us to keep up with our daily processing and ensure the quality of our data before it ever gets to our clients. So now that all the fun stuff is done, it was time to go live. And this is a fairly large challenge in itself. So as I was saying, our daily production of data is something that runs pretty much throughout the day, which means there's a fairly short window in which you need to make this cutover happen. We had 12 terabytes of data sitting on-prem, and you're certainly not going to move 12 terabytes on the day of your cutover. So the one advantage we have of AWS is we were actually able to go in and essentially stand up our parallel production environment 2 months before our go live. And what that allowed us to do was we actually brought over a bulk of the data essentially way before the cutover and leveraged that parallel production to then just do delta copies on a daily basis. And we wrote a lot of custom scripts and automation to actually manage those delta copies on a daily basis. The other thing it actually allowed for us is that parallel production essentially became our UAT, where day in, day out, we could essentially compare the output of the data one-to-one with our on-prem production to make sure that when we go live on the last day, we knew the data would be right. So net-net, this actually got us through a fairly seamless cutover in less than a 12-hour window without disrupting any of our BAU activities. And our clients had no idea whether that came from on-prem or cloud. There we go. So I showed you the 3 boxes for our components in the beginning. Post-migration, this is what our service looks like within our broader platform at this point. You still have the collection systems on the left. You still have the client applications on the right. But what you see now at the heart of it is our data processing that is now split between EMR and Redshift. But in the bigger picture, what you now see is that while before we were doing this handoff of data from left to right, from one component, one system to the other, with our migration to cloud for our larger platform, this entire service now sits on top of a single data lake, which means now we have a single source of truth. Both our Redshift and EMR services integrate very well with our data lake solution. And this just makes the handoffs from left to right just far more seamless and easier to manage. And then above all of that, we can build our end-to-end orchestration, our CI/CD pipelines that are managed as a service. So what I talked to you earlier about how we leverage Airflow, it's not just managed for this migration, it's not just used for the migration that we did, but it really offers that seamless end-to-end orchestration from left to right for our entire platform. So before I wrap up, I just want to leave with a couple of key learnings out of this migration. First and foremost, what was really critical for us was automate, automate, automate. I talked about how 2 months before the cutover, we had to stand up this parallel environment. We were mimicking our cutover day in, day out. We were mimicking our production day in, day out. We spent quite a bit of time to automate that process for managing, bringing up the environment, and tearing down the environment. And that saved us a lot of time. Our partnership with the AWS solution architects was very key. They helped us get through a lot of bottlenecks that we had run into. Spending time up front on establishing a clean baseline was very key to us, especially when you're going from an on-prem solution to a cloud-based solution. Things just don't quite behave the way you would think they would, just because you may have some legacy debt and you may not know your legacy system as well. So investing some time on establishing baselines on the new service is very helpful. Leveraging AWS for what it offers was actually a huge value add for us. Because we were hardware constrained in our past world, one of the challenges we always had was that if we ever had to reprocess data, we ran into this contention where you either had to go get new hardware to reprocess something so that you don't impact your daily production, versus now that we are on cloud, we can just spin up that parallel environment, deal with any reprocessing without ever having to worry about our daily production. Cost optimization is very key. I didn't really talk about it as much, but after we were able to put together our final architecture, we were really able to heavily leverage what AWS had to offer in terms of leveraging reserved instances for our persistent nodes, for our production Redshift cluster, which really helped reduce and manage some of our cost. And for our lower environments, we heavily leverage Spot, which further helps manage our cost around the solution. And last but not least, don't go big bang. Doing this thing incrementally, iterating is really the key, because you learn a lot as you go through this in small chunks. So with that, I'll hand it back to Tony, who'll go through some overview on additional services.
Thank you very much. All right, so just a handful of extra resources and such for you guys for learning and continuing on your own. There is on GitHub, AWS Labs, there's a section dedicated for Redshift. The admin scripts and the admin views on here are particularly important. They're managed primarily by the SAs, the database engineering team on Redshift. We use these scripts all the time when we're working with customers, and they're scripts and views that we have found useful, and we've put them onto GitHub. And they've been there for some time, but we do continue to update them and such, and I highly recommend checking those out. They're a great way to actually learn the system tables and the internal tables in Redshift. If you can see what we've written in the SQL and how we query those tables as well. Next are a series of blogs here. The top one I really like. It is a playbook, design book. It goes through pretty much every aspect of Redshift. It's a 5 It's 5 blogs, so it's a series of blogs, and that's the first one that starts it out. The top 10 performance tuning techniques. If you missed the deep dive session that was earlier this week on performance and getting best practices, this is a really nice, just concise top 10 list of those best practices. We also have, if you are leveraging Spectrum or want to leverage Spectrum, there are some best practices that are unique just for Spectrum as well. Additionally, there's the training inserts. There is also training insert stuff on Redshift now, the big data specialty cert and our upcoming database specialty one, which is in beta right now. So that's what I'm going to leave you with. Thank you guys so much. I hope you've had a good reInvent.